In this video, we will look at hyperparameter optimization, which is one of the important aspects of training a deep neural network. So, in general, the performance of the network depends on how well you train it, and one aspect of the training is to fix the various hyperparameters involved in constructing a deep neural network. Okay. So, this would involve parameters like the number of hidden layers, or number of units per layer, or number of filters per layer, if you can think of it that way. What kind of activation functions to use, if you are using some kind of dropout regularization, how much to use that, what kind of regularizer to use, L1 or L2, and what is the strength of the regularizer, what learning rates that you would like typically do, the weight decay, and of course initialization. We will look at this as a separate topic. We will not touch this here, but we will look at how to do weight initialization later on in a later video. A wrong setting, in this case wrong setting is I would say it is more like a not an optimal setting, could actually affect the performance of a network. Okay. In many ways, in the sense it would converge to a point where it is not giving you very high accuracy in terms of the classification, or the loss function does not decrease beyond a certain point, or in other cases very slow convergence if you do not have optimal values. So, this is a portion, this part of the network optimization is what makes the training of a network very hard. Okay. So, in the process, if you are doing a much simpler network, let us say a couple of layers or 2 to 3 layers, in general that is easier to optimize, you can do that by hand per se. But as the number of layers become large and the size of your data set grows, in general it becomes very difficult to determine what exactly you have to choose as these hyperparameters. So, typically there are two methods that are recommended. I say more like heuristic than method. We will look at one of them, it is called grid search. The idea is to train the network with each possible combination of a hyperparameter. Okay. And needless to say, as your number of parameters increases, then the computations and all will become much higher. Remember that if you have a slightly deeper or larger network, then you actually have to train the network with every choice of these parameters. Okay. And then of course, you would have a holdout data set, or called a validation data set, which you would use to see which parameter setting gives you the best results in terms of, depending on your task that the neural network was set to accomplish. Now, this way of doing it, this hyperparameter search, grid search, in a very systematic way. So, in this case, if you see if the columns are hyperparameter 2, then for a fixed value of hyperparameter 1 you would change hyperparameter 2, and that will be the only variable, and that is one way of doing it, and then you would fix that and change the hyperparameter 1. So, that is one systematic way is you would hold all other, it is a greedy search paradigm wherein you randomly initialize all the parameters that you are trying to optimize, and just vary one systematically, see which gives you the best validation result, and take that value of that hyperparameter, keep that fixed, and then go to the next one, change that, and so on and so forth. Okay. So, this kind of greedy search is possible in a grid search scenario. However, as the number of parameters increases, then the number of times that you have to do this experiment goes up exponentially very quickly. So, it is very easy to see here, right. You have 2 parameters, you have 6 values for every one of them. So, that is like you have to do 36, and if you have 3 or 4 or 5 and each of them has 6 combinations, then you see that is like 6 raised to 5, right. So, it will be this is for 2 parameters, you get, if you have 5, then it is pretty much 6 raised to 5. Okay. So, number of options increases, number of operations increases. Now, another thing to look at here is the scale of the grid search. So, what we meant by grid search was, so if you have a certain range of your parameters. Most of the parameters except for the number of layers or the number of activations per layer or the number of filter kernels are continuous. So, for instance, a learning rate or some weight decay parameter that you have to discretize in a, let us say, a very meaningful fashion. So, for instance, if you are looking at, let us say, learning rate, just for the sake of argument, then you can set the learning rate to 0.01 or, and then you can set it to 0.015, so on and so forth. But then if you see, these are of the same order of magnitude on the same scale. So, one trick is to set all of these in a log scale. Okay. That is one way of splitting the grid. So, this grid search method typically works very well for smaller networks where you do not have as many parameters to optimize, and it is also cheaper to do these computations in a brute force manner. Okay. So, as your search space increases exponentially, as because you have more and more number of hyperparameters to optimize, the better method would be to do random search. Here, instead of training on all possible configuration, you just choose at random. So, it is just the same grid, you can make the similar grid and then you would try to sample, different areas of the grid, okay, just to get an idea of what kind of results you get for each of these points that you have chosen. Now, once among these 5 points, let us say that I have clicked, let us say this one gives you the best result, right. What you can then do is search much closer to this point, see for a better option, if that is possible. One, the way this computational savings happens is that if you recall from the grid search argument, you have to hold all the parameters the same. Let us say you have 6 parameters, you keep constant 5 parameters and you have to change 6 continuously depending on your grid discretization. That means that you are repeating calculations for the same parameter value numerous times. So, that does not happen in a random search. However, it is important that you sample your search space intelligently, so that you are able to cover most of the space in a reasonable fashion. Another thing to look out for is that when your best result corresponds to something at the edge, so this is the edge of your hyperparameter grid, then it is also better to actually increase the grid to the left, or in that case if it is over here to the right, and search a little bit more, because it is possible that there are better values of settings of the hyperparameters available beyond that value. Okay. So, the two important takeaways are that you discretize your hyperparameter values on a log scale, and you construct a grid. This grid again can be made based on what kind of values you would expect to be meaningful depending on the context of the problem. Or you can look at some literature survey and see what typical values are used in networks that have shown good performance. So, the ImageNet architectures are pretty good pointers that way, and most of them do a random search in order to get to a point where they can initialize with the correct hyperparameters. So, there is another way which is I would call this hand tuning, which is not highly recommended, which is again very similar to the grid search, but you do not do it in a very systematic fashion. We just do this to see if there is a trend. Okay. So, for example given there, so if you have an MLP and if you have 50 neurons in all the layers and you get a accuracy 65%, and then you double the number and you get an accuracy of 82%. That is a positive trend. Then maybe you can just be a little bit more adventurous and train with 200 neurons, and then maybe you get accuracy of 84%. Maybe that is a diminishing returns there. So, then maybe you see that okay, this is maybe then it does not make sense to go beyond, let us say 100 or 150 neurons. Okay. So, you can use this kind of strategy to figure out the limits of your grids, okay. See where you can start from so that you get a reasonable result, and then maybe make a grid at that time and either do a random or systematic grid search. So there is one more advanced technique, we won't go into this in detail, which makes use of a machine learning framework. So you have another learning has a learning program or learning strategy to figure out the optimal hyperparameters. Here people use Gaussian processes to figure out in the space of hyperparameters what your validation accuracy looks like, and what the accuracy on your validation data looks like. So that is the function you are trying to fit, the sense that the loss or the validation performance, the performance on the validation data as a function of the hyperparameters. So if you estimate that function using Gaussian processes, then you can find out the optimal value of the hyperparameters, which gives you the best possible result on the validation data.